Welcome to lecture 16, where we will continue with Amadahl's law little more. Let us start with an example where we see that the total execution time of a typical program is made up of 60% of the CPU time and 40% of the IO time. So, out of total number of tasks, we are dividing into two types. One is CPU bound job, another is IO bound job. So, CPU bound job is taking 60% of CPU time and another is taking, IO bound is taking 40%. So, let us see this overall thing where CPU IO, CPU IO, CPU IO, and we assume that there is no overlap between CPU and IO operation. That means when CPU is using, only CPU bound job will be taken care of. When IO bound job is getting performed, only IO bound jobs will be taken care of, and so on. So, we want to see that in this particular scenario, there are two alternatives that we are trying to improve the performance. So, we want to see which one is better. So, first one is increase the CPU speed by 50%. So, we are increasing the CPU speed by 50%, and in another case we are reducing the IO time by half. That means, when we are increasing the CPU speed by 50%, we are not doing anything on this 40%, and when we are reducing the IO time by half, so we are not doing anything on this 60%. So, let us see this. Firstly, increase CPU speed by 50%. So, here F clearly is 60%, 0.60, and S will be 1.5, because speed of 50%, we are increasing 50% more, 0.5, 1 plus 0.5, so it is coming to 1.5, and so overall speed up will be how much? 1 divided by 1 minus F, that is 0.40, plus 0.60 divided by 1.5, that is, this is F divided by the speed up, we are getting 1.25. Similarly, we say that we reduce the IO time by half. So, as you are reducing IO time by half, that means the speed up you are increasing by a factor of 2. So, in this case F is 0.40 and S is 2. So, F is 0.40 and S is 2. You put it in the formula of speed up, where we put 0.60 as 1 minus F, and this is F by S, and we are getting same. So, what we can see that both increasing the CPU speed by 50% or the IO time by half, we are getting the same result. So, both alternatives result in the same speed up, as what I said just now. Let us take another example. Suppose that compute intensive bioinformatics program is running on a given machine X, which takes 10 days to run. So, it is compute intensive, lot of computation is going on for this program, and it is taking 10 days to run. The program spends 25% of its time doing integer instructions and 40% of the time doing IO. So, 25% of the time is spent on doing integer and 40% of the time doing IO. Which of the following two alternatives provides a better trade-off? The first one is use an optimization compiler that reduces the number of integer instructions by 30%. Assume all instructions take the same time. So, firstly, the optimization that is being done is by reducing the number of instructions by 30%. And the next one is we are optimizing the I/O subsystem that reduces the I/O operations from 10 microsecond to 5 microsecond. That is again we are saying a speed up of 2. Let us see the two alternatives. So, in the first case f is 25% and s is we are reducing that by 70 because 30% is reduced and the program spent 25% of the time in integer operation. So, s becomes 100 by 70. So, 0.75 there is no change on that, and 0.25 we are making a change, that is divided by s, which is 100 into 70 or into 70 by 100. So, we are getting a speed up of 1.08. Let us take the next alternative where I/O bound job is 40% and the rest 60% we are not doing anything, but on that 40% we are having a speed up of 2. So, in this case if we solve for the speed up equation we are getting 1.25. So, in this case we can say that alternative B is better than alternative A, where here the speed up on 25% is made and here the speed up on 40% is made. Let us move on with Amadahl's law, Corollary 1. What it says is make the common case fast. What do you mean by common case? By common case we mean that most time consuming and not most frequent. So, let us understand this. There are two things. One is when we say that we are more frequently doing something, but more frequently which we are doing, it is taking less time. But the most common means it is consuming the most amount of time. So, it is most time consuming. So, according to Amadahl's law, improving the uncommon case will not result in much improvement. Rather, if we make improvement on the common case, the improvement will be much more. That means, the portion of the task which is taking more time, we will try to improve on that part rather than which is more frequently used, because most frequently that is used, that is not taking much time. So, the common case has been determined through experimentation and profiling. So, how we can say that this part is common? That can be determined through experimentation and through profiling. When optimizations are carried out, a case that was common earlier may become uncommon later or vice versa. So, you need to analyze the program, you need to analyze it over time and again to understand this. So, when we are saying common part means most time consuming part. So, you have made some improvement and you have reduced that time, and then again if you can finally say that okay, now once this common part I have reduced the time, next time when you do that it might change. So, this particular phenomena it says that when optimizations are carried out, a case that was common earlier may become uncommon later, because you have already taken care of that particular case. So, Amadahl's law corollary 2 for latency, what it says, let us see, L new equals to L old by speed up. So, by Amadahl's law, L new equals to L old into 1 minus f plus f by s. So, this is speed up is 1 divided by this, so it goes up, this into this. So, we can also write L new as L old into f by s plus L old into 1 minus f. We have just multiplied these two. Let us see this Amadahl's non-corollary. So, here what it says that Amadahl's law does not bound the slowdown. That means, we are always saying that a part of the program where improvement can be made and you can finally get an overall speed up of this much. But what if those portions where we are not making, if you slow down that particular portion, then how it will affect? So, the parts which are not used so much and you are trying to further make some techniques such that that particular part will reduce. I mean, the performance of that part will further reduce. So, you are not making any speed up on that and you are making something such that that performance of that part will further reduce. Then what will happen? So, things can get arbitrarily so slow if we hurt the non-common case too much. Not the common, but the non-common case too much. So, we should not do that as well. So, those portions which are not so common, we cannot hurt that too much. So, we will see this example. Suppose f is 0.01 and L old is 1. Now, we are making a part 100 times worse. So, this becomes, the speed up becomes 0.001 on the uncommon part, that is now your f. So, L old will become multiplied by 0.01, that is f divided by s, plus s L old into, this is 1 minus f, that is 0.99. So, how much it is coming? It is coming 10 times the old value. So, L new is 10 times the old value. So, it has worsened. And in case 2, if it is 10 to the power 5 times worse, then what is happening? Finally, we are getting 1000 into L old, which is even worst. So, we cannot just make the non-common part, we cannot make the uncommon part too much bad. So, if we make that uncommon part too much worse, then the situation will become bad. Now, let us see this extension of Amadahl's law to multiple enhancement. By multiple enhancement, what we are meaning is that here earlier we were saying that we have a total portion and out of which one part we are making some improvement and other part remains the same. Now, let us say in a computation we have IO bound job, we have CPU bound job, we have some other kinds of job as well. And now we are making improvement on these bounds. So, earlier we were just making improvement on one, now we are saying that we will make improvement on these as well, others as well. So, in that case what will happen? How this multiple enhancement can be taken care in Amadahl's law? Let us see. We have already seen for one part, one fractional part, if we improve, what final speed up we will gain. Now, we will see that we have multiple parts and we are improving multiple parts, and now how much you will gain. Suppose we carry out multiple optimizations to a program. So, optimization 1 speeds up fraction f1 of a program by factor s1. Optimization 2 speeds up fraction f2 of a program by a factor s2. So, f1 and f2 are two fractions on which we are making the improvement now, on which we are making improvement s1 for f1, s2 for f2. So, this is the part where no improvement can be made, and this is a part on which we are making improvement s1, and this is a part where we are making improvement S2. So, earlier it was taking F1 and F2 and it has got reduced, and now we are getting F1 by S1 and F2 by S2. So, similarly, what will be the speed up? The speed up formula will be same, 1 divided by 1 minus F1 minus F2. Earlier it was only 1 minus F. Now it is 1 minus F1 and F2 plus improvement on F1, that is F1 by S1 plus F2 by S2. So, this will be the total improvement when we are saying that we have multiple enhancement. We are not making enhancement on a single portion, rather we are making enhancement on both the portions. Now, let us say in the calculation as shown, it is assumed that F1 and F2 are disjoint. So, in this particular case, F1 and F2 is disjoint, and what we are doing that we are making improvement on this part only and this part only. But now let us say there can be a situation like this. So, in this situation what happens? This is your part which says this is your F1 part, and this is your F2 part, and your this part is having both F1 and F2. So, this part enhancement can be taken care separately, this part enhancement can be taken care separately, this part and this part separately. Earlier it was having disjoint. So, earlier the case was this was one part, this was another part. So, this is considered F1 and this one is considered F2. No common part was there. But now we are extending F1 till here and we are extending F2 till here. So, this has become now the common part which contains both F1 and F2. Now, under such scenario, let us see how we will calculate the speed up. So, S1 and S2 do not apply to the same portions of execution. If it is not so, we have to treat the overlap as a separate portion of execution and measure its speed up independently. Now, this is very true that this is one part, this is one part, and this should be also considered another part, and we have to calculate the speed up separately. Although we have a common part of both, F1 also is here and F2 is also here, but we have to take care of this. If it is not so, we have to treat the overlap as a separate portion, as it is not disjoint. So, we have to take care this part and this part separately. So, in this case what will happen? This is the portion where no change will happen, and these are the three portions where you are making some changes, where this part is F1 only, this part is F2 only, and this part is both F1 and F2. So, what we are doing? F1 only by S1 only, F1 and 2 with S1 and 2, and F2 only with S2 only. So, it was initially this much, after this reduction it has become this much, initially this much, after reduction it has become this much. So, finally, the speed up equation can be said as 1 minus F1 only minus F2 only minus F1 and F2. So, we are taking into consideration all the parts plus F only divided by S1 only plus F2 only divided by S2 only, and then taking into consideration both 1 and 2 divided by S1 and 2. Now, this is the general expression just now what we have said. So, we assume m enhancements of fractions, that is F1, F2 up to Fm by factors of S1, S2, Sm respectively. So, in that case what will happen? The overall speed up will be 1 divided by 1 minus summation of all these FIs. How many enhancement will be there? Those many FIs will come here, plus summation of Fi divided by Si. So, this is a general expression of speed up when multiple enhancements are taken into consideration. Now, let us take an example. So, although we have not discussed about cache memory yet, so I can just tell you that cache memory is a fast memory that sits between CPU and your main memory, and it is used to enhance the overall improvement of the memory, overall speed up of the memory. So, consider an example of memory system where main memory and a fast memory called cache memory is used. So, this is your cache memory, this is your main memory. Frequently used parts of the program or data are kept in cache memory. So, in cache memory we keep frequently used instructions or data. And use of cache memory speeds up memory access by a factor of 8. So, whenever cache memory is used, then the speed up factor is improved, that is speed up of memory by a factor of 8. Without cache, the memory operation consumes a fraction 0.40 of the total execution time. So, without cache, the memory operation consumes a fraction 0.40 of the total execution time. So, what will be the speed up? So, in this case, as without cache memory it was taking this much. Now, using cache memory you can actually make a speed up on this 0.4. How much speed up? 8, and the remaining will not change. So, if you put this in the formula of speed up, you will be getting 0.91. Let us take another example here where we consider two levels of cache memory, where we say that the first level is called L1 cache and the next level is called L2 cache. What is the assumption? The assumption here is without the cache memory, without the cache, the memory operations take 30% of execution time. When no cache memory is used, memory operation is taking 30% of the total execution time. When L1 cache is used, it speeds up 80% of the memory operation by a factor of 4. Now, out of total execution time, only memory operation is 30%. Now, out of that 30%, if when L1 cache is used, 80% of the memory operation by a factor of 4. And the L2 cache speeds up 50% of the remaining 20% of the memory operation by a factor of 2. So, there are two things. Out of total execution time, the memory operation is taking 30%. Out of this 30%, now 80% of the memory operation are found in L1 cache and 20% of the memory operation is found in L2 cache. And it's 80% of the memory operation, L1 cache actually speeds up 80%. So, when L1 cache is used, 80% of the memory operation is improved by a factor of 4, and when L2 cache is used, 50% of the memory operation is speeds up by a 20% memory operation by a factor of 2, because this is 80%, so the remaining 20% of the total 30% is 50%. So, L2 cache speeds up 50%. We want to find out the overall speed up. Let us see how we can find out the overall speed up. Memory operation 0.3, 30%. So, FL1 will be when L1 is used. So, as I said, L1 is used 80% of the time out of this 0. So, 0.3 into 0.8. So, 0.24 will be when FL1 is used, and the SL1 is 4, which is already given. Similarly, for FL2, that is 0.3 multiplied by, it was 80%. So, this will be 20%. Out of 20%, it is 50% used. So, 0.5, that is coming down to 0.03, and SL2 will be 2 by a factor of 2 by a factor of 4. This is 80% and the remaining 20% 50% improvement. So, remaining 20% 50% improvement we are making. Now, we will put this value here, 1 divided by 1 minus L1 minus L2 plus L1 by SL1 F L2 by SL2, and we are getting a speed up of 1.24. So, we came to the end of lecture 16, and which will end the week 3 lectures. So, in this week we have actually seen the performance, how we can calculate performance, how Amadahl's law is actually happening, and how it is helping us to determine that how much speed up can be actually achievable, provided only a part of which you are actually making the improvement, when you are only making improvement in a part of it.